The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
The pH titration curve for titration of 25 milliliters of 1 molar ammonia with a 0.1 molar hydrochloric acid. Okay, this time what's going to end up happening is if we look at our setup, our initial setup, right, we're going to have the acid, we're going to have the base in here, the ammonia, and then we're going to have actually our acid in the BRA. Okay, great. So if we take a look at the reaction here, we see that the hydrochloric acid is going to react with the ammonia, and that's going to give us an ammonium ion, right? And that ammonium is then going to go on to react with water, and that's going to give us base, and it's going to give us hydronium ion, right? Now, because at the end of the reaction, we're being left with the hydronium ion, do we think that the solution is going to be basic, neutral, or acidic? Well, it's going to be acidic, right? Because at the end we're going to have hydronium. Okay, great. So what we'll do now is we'll just go ahead and we'll talk about the various ways we can calculate the pH at different points during the titration curve. Initially, we'll first calculate the pH of the ammonia that's in the Erlenmeyer flask prior to us adding any acid, right? And how can we do that? Well, we'll just go ahead and do that now on the next slide. Before the addition of strong acid, we can just go ahead and do it like we were doing in the previous lecture. We'll just go ahead and start with our base dissociation constant. This time it's given to us, even if it's not, you can find it in the table, and that's going to be 1.8 times 10 to the power of negative 5. I'm not going to go ahead and do the ICE table, as you'll still get the gist of it from this. And then our hydroxide ion concentration over our ammonia. Okay, great. Now we can go ahead and just write this in as x squared. And what is our ammonia concentration? Well, they're telling us that it's going to be 0.1 molar, right? If we just go back, they told us that it's going to be a 0.1 molar ammonia solution. Wonderful. Once we go ahead and we fill that in, minus x, right? Here we'll just make the assumption that x is actually going to be less than 5% of our initial concentration, right? And once we go ahead with that assumption, we get the following, right? Great. From here, we can go ahead and we can calculate x, which is also going to be our hydroxide concentration, right? There we are. And that, once you go ahead and you calculate it, will be 1.34 times 10 to the power of negative 3. Once you have a hydroxide concentration, what are we going to do next? Well, you can go ahead and get the POH, and then from the POH, we'll go ahead and we can get the pH. So let's go ahead and do that. We're going to now go ahead and get the POH, right? And the POH is just going to be negative log our hydroxide concentration, which is going to be negative log, right, 1.34 times 10 to the power of negative 3. This gives us a value of 2.87. And are we done yet? No, we're not done yet because we don't have the pH concentration. Let's go ahead now and find our pH concentration. pH, as we've been saying, is just 14 minus our POH, right? Thus, 14 minus 2.87 will give us a numerical value of 11.3. That's before we add now. This is going to be the new, this value here, 11.13. Before we add any HCl, our value here is going to be 11.13. Okay, great. Now what we'll do next is let's calculate the half equivalence point. That's what we'll do next. Okay, because we're going to have 25 milliliters of our base here, ammonia, right? We know that at the half equivalence point, we're going to have 12.5 milliliters of hydrochloric acid added, right? And 12.5, if we go ahead and we do